Well, hello there. So let's look at using phasor techniques to solve circuit problems. So in the last module, you learned how to come up with impedances. It's a function of the component values and the frequency. And we know how to find the impedance of resistors, inductors, and capacitors, how to convert sinusoids for our sources, our voltage sources or current sources, into the phasor form. And now we're going to use those techniques to solve circuit problems. So here is the process that we're going to use. So remember, in the beginning, you need a positive amplitude and a cosine term. So sines to cosine, you just subtract an extra 90 degrees of phase. And if you have to flip the sign here, the plus or minus sign on the amplitude, then you would put a 180 degree phase shift. For resistors and capacitors, we're moving to just the impedances. So Z is from these equations here. Then we solve using impedances just like resistors. And then when we're done, we have a phasor for the solution, so we have to transform back from phasors to the time domain. So here are some examples of just combining impedances. So when we have components in a circuit, they're all impedances. So whether they're resistors or inductors or capacitors, we can combine them together using the same rules that we would use to combine resistors. So these two components are in series, so R and L, you would just add them together. They're all in series in this circuit, but here's an RC circuit. Remember, the impedance of a capacitor is negative J over omega C, so there's a minus sign here. Inductor and capacitor in series get combined together. Both of these are purely imaginary, so you get something with just an imaginary term here when we do it. These are all in the rectangular form because that's what comes naturally from combining these when we're adding them together. But you could convert them to polar form if you wanted to. Normally we're going to deal with just impedance, and I think that's the right thing to do. So impedance is equivalent to resistance. The 1 over the inverse of impedance is called admittance. So Y is 1 over capital Z, and I don't know why you need a separate term just for 1 over, but it's here and you should see it. It'll come up in a few examples. So be very cautious if you see Y, that's 1 over Z. So things we can do with impedances are the same things we can do with resistors. So it's easy to solve for a circuit like this with two impedances in series with a voltage source. And we can come up with the voltage divider equations. Normally we are solving for V2, the one that has the same common ground node as the source, Z2 over Z1 plus Z2 times Vs. But the voltage across this impedance, V1 with the minus sign here in the middle, is an equivalent looking equation. Current division, when we have two impedances in parallel, the current gets divided between the two. And the equation here, notice these are Y's. They're the admittances and not the impedances. So remember, Y is 1 over Z. So take that into account when you're using these equations. Okay, so let's look at some examples. This one has a circuit with a voltage source, a resistor, capacitor, inductor, and another resistor. And we're trying to find the impedance of the circuit, given the component values, and the voltage across R2, this is labeled V2 right here. So this is the time domain. We move it to the phasor domain by writing impedances for each of the components. So Z1, ZL, ZR2, where Z1 here is already combined, the R1 and the C together. So Z1 is R1 minus ZC, or plus ZC, and ZC is negative J over omega C. So then these two would be in parallel, and we would, to get a Z2 here, ZL in parallel with ZR2, and then we would add them together at the end. So just like you do with resistors, pick two that are obvious, replace them, find another two that are obvious, replace them, and eventually you'll simplify the circuit. The math is done here, and it's just as important when we're talking about these concepts. The concepts you're probably familiar with, but going through the math with your calculator is really important because it's not something you're doing a lot with complex numbers and phasors. So make sure you put the numbers in your calculator when you're looking at these examples and figure out how to do it with MATLAB or with the I button on your calculator. So given some numbers, we can solve for all the values and compare the numbers with the solutions here. So this is our final ZI in the rectangular form in kiloohms. And the voltage across that resistor is the same as the voltage across this combined Z2 that was the two because they were in parallel. They'll have the same voltage. So you can use the voltage divider equation with phasors to come up with this. So again, put all these numbers into your calculator to make sure you're getting the same answers. And then converting back is easy. Once we have the amplitude and the phase, we put the amplitude here, we put the phase there, and we have to put omega back into our equation. So all of the other things that we've been doing with resistors, like Thevenin and Norton equivalent circuits, we can do now with impedances. So we can find a Thevenin equivalent, a voltage source with an impedance in series. That's the equivalent of any black box with two wires coming out, as long as we're using sinusoidal sources everywhere. And node and mesh analysis also work. It's worth talking about phasor diagrams. This is the complex plane with the imaginary axis and the real axis. And when we're dealing with phasor quantities, we can also write them graphically. So maybe there was a time when everyone didn't have a scientific calculator that could do trig functions, and you could actually write out phasors and add and subtract them together using vector math, adding them head to tail and that sort of thing. So writing them out with a protractor and a ruler on graph paper is a different way to solve this. Because calculators are so much faster than doing it that way, we don't do it that way anymore. But you'll see phasor diagrams. They're a good way to see what's going on, to check your numbers, just to have a whole different way of looking at your solution. So capacitor, J omega C times VC. If VC is on the real axis, then that's going to be a real number. And so IC is going to be purely imaginary, going up here. And you can solve for any quantity I or V, and you can draw this. It's in the negative J direction, so IL is going down. This is an example of looking at things like VS as VR plus VC plus VL. So this is Kirchhoff's voltage law. Of the sum of the voltage around the loop has to sum to 0. And so we get this equation. And you can add them up as a vector. So here's VS, and here's VC, and VL. They're opposite in phase to each other. And VR is perpendicular to those two because one would be in the imaginary and one would be in the real, but there's a different phase. So if you add these all head to tail, you end up with VS here. If this doesn't help you, that's okay. Learn how to do it with your calculator and check your numbers. All right, well, I hope you learned a little bit, and you're going to have plenty of homeworks to practice, and we will do some more examples in the next video. So let me know if you have questions, and I'll see you in the next video.